Good day and welcome back to part 3 of our discussion dealing with double integrals over general regions. In the previous video we introduced the idea of what is a type 1 or a type 2 region. And remember, you don't need to memorize exactly what these definitions are, but it's more just developing the thought process that we would use to come up with limits of integration for our iterated integral. And in this video, we will focus on the idea of how we can switch the order of integration. That is, change our perspective maybe from being type 1 to that of being a region of type 2. And I would like to begin by just illustrating with an example. And here, irregardless of our function of integration, what I would like to do is think from these limits of integration, what does the region look like? And note that because of the order of integration, we have constants on the outside. So I'm going to think in my region the x values are varying from 0 to 4. And then those inside limits of integration are telling me if I pick any generic value of x I would like between 0 and 4, how do those corresponding y values vary? And they vary along these horizontal line segments going from the lower curve, y equals 0, to that upper curve, y equals the square root of x. And note, for this curve y equals square root of x, this upper right point of the region would be the point 4, 2. So if I wanted to switch around and think about this region now as being a region that's varying in that horizontal direction, we have our y values on the outside as varying between 0 and 2. And then on the inside, we need to think, how do our corresponding x values vary? So if we pick an arbitrary y between 0 and 2, our x values vary from that lower blue curve to that upper line segment. And remember, in terms of equations, we're thinking, how are the x values varying? We go from a lower curve x equals to an upper curve of the form x equals. The upper curve, considering that this is a point 4, 2, is the vertical line x equals 4. And the lower curve would come from solving for x in the equation y equals square root x. That is x equals y squared. And note our limits of integration. We go from y squared to 4, y squared to 4 in that x direction. And even though we can switch around that order of integration, irregardless of the function, you may be wondering, why would we want to? What is the need for us to do so? And it turns out there could be a great need for us to do so, in the sense of example number 4, that if you wanted to evaluate the antiderivative of e to the x squared, we are unable to do so with respect to x. That is, this inside integral is impossible for us to evaluate, which means the only thing that we could do is switch around the order of integration so that we first integrate with respect to y and second integrate with respect to x. And the reason that would be beneficial is because with respect to y, e to the x squared is a constant, which is the easiest possible quantity for us to deal with. So let's see if we can do this. We're starting off with this integral from 0 to 1, 3y to 3, e to the x squared. And our order of integration is dx dy. And what I would like to do is write this in an equivalent way, where instead of integrating in the order dx dy, we switch that order to dy dx. And our process for doing this is to sketch the corresponding region of integration and then just view it from that different perspective. And this is definitely going to be an acquired skill or technique, something that requires practice. So note, when I'm sitting up this region, I'm really thinking from the outside, working my way in. The y values are varying from 0 to 1. So on the outside, we have 0 to 1 in terms of our y values. And then what we need to think about is, for a value of y between 0 and 1, how do those corresponding x values vary? they vary from x equals 3y to x equals 3. So let's sketch these curves. And x equals 3 is maybe the simpler thing to sketch. It's just a vertical line. In terms of x equals 3y, it might be more convenient to write this as y equals 1/3 x, where y equals 1/3 x is a line going through the origin with slope 1/3. So the line segment drawn is x equals 3y. Now to get our region sketched, we have on the outside limits of integration the numbers 0 from 1, for which the y values vary. Now we work to the inside. We think for a y value between 0 and 1, how do the corresponding x values vary? They vary from the lower curve, x equals 3y, in that x direction until you hit the larger curve, x equals 3. So our x values are varying from x equals 3y to x equals 3 along these horizontal line segments. And really, for me, the best way to think about this is to sketch those horizontal line segments. Now, instead of viewing this as being made up of a bunch of horizontal line segments, which is, I guess, what we would call a type 2 region, let's go ahead and think about this as being made up of a bunch of these vertical line segments, i.e. one of these type 1 regions. So I'm going to redraw the picture, and then we'll kind of label everything appropriately. So we have x equals 3, y equals x over 3, and we know this point of intersection is 3, 1. If we want to put x on the outside, those would be the numbers for which the x values in our region vary from. We vary from the lower value of x at 0 to the upper value of x at 3. So our lower limit of integration is 0, our upper limit of integration is 3. And the question is now, if I pick a generic value of x between 0 and 3, how do those corresponding y values vary? Well, you vary from a lower y value on the x-axis, so we think y equals 0, to an upper value determined by this line, y equals x over 3. So thinking about how our y values vary by drawing vertical lines, we vary from y equals 0 to y equals x over 3. And this idea of first recognizing that we need to switch around that order of integration, and then doing so by sketching the region of integration and changing our perspective, is a very important process. Without being able to go through this, this is certainly a double integral we would be unable to evaluate. And I would also like to note that when we see an example like this in the future, we may not give you the hint that you need to switch the order of integration. Part of the thought process is going to be realizing that we need to switch the order of integration. Let's go ahead and evaluate this integral. Now that we are integrating e to the x squared with respect to y, we can think of it as a constant. So we would have e to the x squared y, and we're evaluating this from y equals 0 to y equals x over 3. So we substitute in y equals x over 3, minus sign, substitute in 0. So we get a 1/3 that pulls out front, and an x e to the x squared that we need to integrate. Because note, when y is 0, that quantity is 0. And at this point, we have something that's highly conducive to a u substitution. If we were to use u equals x squared, du is 2x dx, so that 1/2 du is x dx. So the x and the dx becomes 1/2 du. X squared is u. We have an extra 1/2 that pulls out front to make it a 1/6. Limits of integration that are yet to be determined, and e to the u du. In terms of our limits of integration, we can just think in terms of our substitution. When x is 0, u is 0 squared, which is 0. Our lower limit And when x is equal to 3, our upper limit, u is 3 squared, which is 9. And remember, whenever we are evaluating a definite integral with a u substitution, as tedious and as unnecessary as it might seem at the moment, we always switch around our limits of integration. When we get to more involved double integrals and triple integrals, you will be very happy that you have done so. So lastly, the antiderivative of e to the u is e to the u. We evaluate from 9 to 0, so we get 1/6 times the quantity e to the 9 minus 1. And this completes our discussion for the current video. And what's going to remain in the upcoming videos is just going through and practicing and seeing more of the subtleties involved with both sitting up and evaluating these double integrals over general regions. And remember, this is always a great opportunity for you all to go back to those suggested problems and practice examples. Reach out and let me know if you have questions. So stay tuned and take care.